Let's go.
Okay. Hello, everyone. We are today in this workshop named Call to Action for Robots Operating System Team Members. It will be in charge of Robert Jackson, Steve Lahr, and Ian Hughes. So welcome. If you have any question, you can leave it on the chat, and then we will answer at the end of the session. Welcome, Robert.
All right. My name is Robert Jackson, and I'm from the OpenR2 project, and I'm here with Steve Lahr. The purpose of this project is to imagine what we could do if we could turn the fan-made replica props that we see at the conventions and at the maker fairs. What if we could turn those replica props into actual autonomous robots? In 2020, we have a unique intersection point where we have the Open Robotics Foundation with the robot operating system, the replica prop form with their manufacturing skills becoming best class. We have the 3D experience platform where we've partnered with Dassault, and we have the Nvidia Jetson line where embedded systems are now affordable. Oh, no. Okay. So in this presentation, we're going to go through a few things. What is our inspiration? Which robots we're focusing on, where we're located, what we've accomplished so far, what's next in our project, why we need more than 3D traditional CAD to make this happen, what kind of teams we're looking for, what are the projects we have in mind. We'll have a question and answer session, and then we'll give a set of links if you're interested in getting involved, where to go from here. So first of all, what is our inspiration? Back in 1997, I worked at a company called Silicon Graphics. They're most known for inventing the OpenGL graphics system that's on most of the 3D computer graphics cards today. My manager's cube actually had this cardboard cutout life-size cardboard cutout was in his cubicle. You had to walk past it to get into his cube and sit down and talk to him. So what I did is I started making all of my projects, all of my demos for OpenGL. The subject matter would be R2-D2. As I got more involved in this, I was able to purchase my first set of blueprints to where I could improve the models. I bought those from Nordic Engineering. That was the engineering company that actually was involved in building R2-D2 in 1976. I modeled that first R2-D2 in CATIA version 4 for OpenGL optimizer demos. From there, I was able to purchase some more blueprints and some more assets that helped me refine my models. A dome from the Empire Strikes Back. We were able to get Vickers Viscount reading lamps. We got a resin dome from Return of the Sith. We've got the die line blueprints from the prop store. About that time, CATIA version 5 came out, and we were able to remaster R2-D2 in CATIA v5 using all the new parametric design, nerve surfaces. We were able to get the leg drop blueprints from the prop store, the center steering blueprints from Caesar's Palace, and then we were able to remaster R2 in CATIA version 6. While we were doing that, we had submitted for a project for the Dassault Systems 3D Experience Lab, which was an accelerator startup plus a collaborative environment startup effort by Dassault Systems. We put in a project that was supposed to get us access to the 3D Experience cloud environment, CATIA, Simulia, Innovia On Demand, mentoring and learning from Dassault, and get us access to some of their events and some of their connections. The way that this process works is you submit your project, and then Dassault Systems employees do a presentation in front of the entire company, and then they select the best projects. We were actually selected in the Innovation Committee number 13 in December 17th, 2018, and one of our supporters that actually selected our project was Bernard Charlet, who is the CEO of Dassault Systems. So in doing this project, the first thing we had the first decision point was which fan-made robot prop replica were we going to focus on. If you go out to the internet, out to Facebook or out to the replica prop forum, there's hundreds and hundreds and hundreds of groups out there that are making replica robots. There's C-3PO, Robbie the Robot, the B-9 robot from Lost in Space, Wall-E, there's the Terminator, and about 14 different flavors of Star Wars robots. So we decided, first off, that we were going to go with R2-D2. In the R2-D2 community, there's still hundreds of clubs. There's 3D printing clubs for R2-D2. There's geographical clubs like the UK R2 Builders Club, Midwest, the Belgian Builders, all things R2. We set up our own club called, on Facebook, let me move this out of the way, called Open R2. So we are an open source R2 Builders Club where the goal is to share everything that all of our content open source. So once we decided on R2, there's actually 7 different R2-D2s that were used in the first film. Some of the R2-D2s had an actor inside, like 1, 2, and 4. Some of the units were just very lightweight props that were for carrying around or lifting, or there was even a half-size prop that went in one of the spaceships. Our focus, we decided, was the number 3 unit, which is the unit that has 3 legs and is currently, and was set up and spec'd to be a remote control unit. This person right here, that's John Steers. He was the original person in 1976 from the production team that was in charge of building these props, fabricating them. And his dream was to have at least one of these props be an actual autonomous robot. Due to the technology at the time in 1976 and due to the time constraints and the budget constraints on getting the movie out, he had to settle for that not being an autonomous robot, but only being a remote control unit. So our goal is to take unit number 3 and really realize John's dream of that being a real autonomous R2-D2. So in order to do this, we've spent about 15, maybe even 20 years collecting source information so that we can actually build this as a replica. The goal is that all of the exterior mechanical, mechatronic components of this be true to the original, but instead of the remote control system, we're going to do away with the remote control system and replace that with Nvidia embedded system hardware running robot operating system. Some of the resources that we have is we have an extensive set of the original production blueprints. You can see that these are fully dimensioned blueprints. These are the real blueprints that they used with the correct numbers to make the robots in 1976. We have some production items like an original dome. We have original found items like the hollow projectors. These are aircraft reading lamps. We have an extensive set of photographs. These are original production photographs that people have given to us to use for reference. And we even have access to some of the original people that fabricated these. This is Neil Anderson in 1976, and he's actually fabricating that particular unit that we're interested in, that remote control unit, unit number 3. The Trilate Unit. So where are we located? We have 2 facilities. We have a maker space in Tennessee. This is the original building before we bought it. And then you can see as we're progressing, turning it into a maker space, cleaning it up. Inside, we have some CNC machines, some CNC lathes, drill presses, paint booths, and we have a welding station. We also have a second facility that we split our time between. This is a facility that's run in Columbus. It's a community group called the Columbus Idea Foundry. This facility is about 10 times the size of our current facility, and has quite a bit more equipment. So what have we accomplished so far? The first thing we had to do was take all of those assets, the 2D blueprints, the production casts, the dome, the found items, and we needed to either use the numbers on the blueprints to draw these in 3D, or we needed to have them laser scanned and modeled to make an online geometry database. So currently we have all the parts modeled in 3D in the 3D Experience online geometry database in the cloud. Some of the major teams that we have inside of the cloud, we've got an RC dome team that are working on making a replica out of aluminum of the RC dome. We have a body project going on. That's Ian's project, where he's finished modeling this completely, and he's gone to his second prototype version. That's this right here is the second prototype. About a month ago, he did the first prototype. The laser cutting went fine, but when he went to roll it, he wasn't really an expert on rolling, and he damaged the skin. So we found out that when you actually take the flat skins and you roll them into the cylindrical shape, you need to roll them between something, either another aluminum sacrificial skin or something like mylar or some sort of plastic that will take the distortion and leave your parts undamaged. So this is ready. He's got this assembled and ready to go to the TIG welder. So by the end of this week, we're hoping that these will actually be welded into a unibody. This is different than what most people have done, but true to the original R2 in that it's put together like an airplane, where you have the outside skins and then frame rails, longerons, and transients that hook all the structure together and make some pretty lightweight components very strong and rigid. This is the neck project. This is my project that I'm working on. This is the original neck rotation. This is what turns the head on the body. Most people make an outside skin and then put something in there like a Rockler bearing, but the actual original bearing from 1976 was a functional bearing. You can see that it's a metal race, exterior race, outer race that's riding on these nylon inside races, and this rotates around on these races. We have the hollow projector project. That's what Steve's working on. He's making a faithful replica of this found part. Like we said, this was originally an aircraft reading lamp. This is one of 3 found parts that are on R2. Most of it was designed in his original content that Lucasfilm developed. But this piece, the brake dampener on the leg drop and the shoulder buttons were actually found items. And we have the leg drop system. This is the leg dampener that I was talking about. That's off-the-shelf item. You can see that here too. This is a project that's in work. This is what drops the center leg down. So there's springs on here, and springs that hook this trolley, and you push it up and clamp it. And then when you want to go from 2-leg mode to 3-leg mode, you hit a switch, and this switch releases, and the springs drag the center foot down, throw the body forward, and it goes from being 2-leg standing to 3-leg remote control mode. And we have another project that's the center foot steering. Most people thought that R2-D2 was actually a differential drive, where the rear 2 feet that are back here have motors in it, and you're just varying the speed in order to steer it. And that's true for later films, but for this first film and the replica that we're replicating, they actually had wheels that were being steered. And this is a really unique design that they had quite a bit of trouble controlling, but we're hoping with the robot operating system, control system in there, and embedded systems, we'll be able to control this and make it work. This is a slider that slides backwards while this slides forward, and that turns both of these wheels in parallel. So this center foot doesn't turn. This is a fixed shell, but these wheels inside both turn in parallel to turn the unit. So what's next? So we have most of the structure done, and we have a prop that's quite a bit along the way where you can buy these parts and put it together and assemble it, and it looks like an R2-D2, but it really doesn't do anything. You could go out and buy some components that are available on the web to make it remote control, but again, our goal is to make this a fully autonomous robot. So the next step is to start getting teams together that are actually going to do the robot operating system programming. We're going to put a backbone system in and get different subsystems up that control different parts of the robot, the motors, the mechanical arms, the rotation of the dome, the motion of the hollow projector, and of course we want computer vision with OpenCV so we can do tracking and we can implement behavior like following. We're going to do that with Ross from the Open Robotics Foundation and the Nvidia embedded systems. We would not have been able to do this about 10 years ago because this board right here would have probably been about $5,000 to $10,000. What's happened over the last 24 months is Nvidia has gotten the price point down of being able to have 128 cores of Nvidia Maxwell GPUs down to $99. So most of our subsystems, like rotating the dome or controlling the motors, are going to be driven off these, which means each team member that wants to do this, the only real investment that they need that's sort of significant is this $100 board. Each group of the subsystems will be controlled by an NX Xavier. This is a little bit more expensive, but it's controlling all of the subsystems, and that's dropped down to $400. The main subsystem that's the main embedded system on a board that's controlling the entire robot is the AGX, and that's $799. This is going to be doing all of the image processing and sending out basically the Ross head node runs on this and does all the communication to down to this node, which then branches out to this node. We have a side project that we want to do that's specific for working with Neil Anderson. Neil is on our team. Like we said, Neil is the original person that drew these blueprints in 1976. He designed this leg drop system to drop this center foot down. He actually was starting on a second rev of this called MK2. So he had MK1 that he built, and he was just getting started on MK2 to address some of the issues, some of the things that weren't quite working right, when they packed up and left for the filming location and took all of his robots away from him. So he never got to finish this project. So he's really interested in getting a second chance at putting his MK2 design together and seeing if we can get this working. He only had 3 weeks to design this, so things like designing these springs, tuning how much tension needed to be on this set of springs and this set of springs, he really didn't get a chance to do any fine tuning at all or fix anything that wasn't quite working right. So with Neil, combined with our team, Neil, and then Dassault Systems using their Simulia simulation software, what we want to do is we actually want to animate this and do an analysis to see, what the acceleration is, what the velocity is, what the forces are on each of these components, and actually allow Neil, what is this, 50 years later, to go back in and redo this and get it working 100%. When they use this on the film and they would actually hit the leg drop mechanism button and drop this leg drop, you would have about a 50% failure rate. The robot, half the time, this foot would just hit the skirt, get caught up, and with that momentum, it would just topple the robot over and do what we call a face plant. So it would just fall face first on the ground. A lot of the damage, if you look at some of our photos, you'll see a lot of damage to this region of the robot, and that's from this leg drop not working and the robot falling over. So in doing this project, why do we need more than just a traditional CAD system? Well, why can't we just use something like Fusion 360 or AutoCAD or SolidWorks or even CATIA file-based? Why do we need a PLM system? The first thing that the first challenge that you have when working with a project like this, where you have a number of teams, in this example, we have 3 teams, one doing the leg drop system, one doing the body structure, and one doing the neck bearing. all of these components fit in the same area and they work together. But the design is done by 3 different teams. So what 3D Experience allows us to do is set up 3 separate collaborative spaces, each one for each team, where each one of those teams owns the data that they're generating in each one of these collaborative spaces. However, they can share that data out to the other teams so that all the other teams are working to their background information and everybody's going forward. In a traditional system, if, say, this part right here, you can see this frame member, this upper frame member. This frame member is being authored by the leg drop team, but it's being consumed by the body team, and it's also being consumed by the neck race team. Neither of these teams can actually change this design. This is locked to the leg drop team. But every time the leg drop team makes a modification, it instantly shows up in each of these other collaborative spaces to be used immediately. Another issue that we have with traditional file-based teams that some of even the earlier attempts at doing this project when we were just doing the remote control unit is, you know, files get overwritten, files get mixed up, they get moved around, you make a change and you don't realize that you're changing the wrong file. So what we need from a PLM system is lifecycle. And what you can see here is we've got the first revision of this neck race that has the threaded studs, the nuts, and the washers, and has a solid outer race bearing. This is our first revision. Once we're done designing with that, we release it. Once that's released, it's completely locked. Nobody can ever change that. That will exist forever, and we can always go back and machine parts from that or reference that or use it in other designs. So that's locked completely. Once it's locked, if we need to make a design change, we do what's called versioning. So we take this first revision and we version it to Rev A. So here's Rev A, where we've changed these dome locating pins from the threaded studs and the bolts and the washers to a locating pin. Once we're done with that, we lock that down by releasing it. So now Rev A can never be changed, and we have both of these versions that we can always reference. Now we get feedback that this is still too heavy and we want to do weight relief to it. So we version the released Rev A and we make Rev B over here. And that's where we drill in our weight relief holes around this unit. So we've got the initial Rev dash, we've got Rev A, and we got Rev B. These are in the database. They'll never go anywhere. Nobody can ever overwrite them. They can never be lost. They can never be mixed up. So that's a real great benefit when we're, a real important benefit when we're collaborating as teams. The next thing that we get is configuration control. You'll notice that each one of these revisions actually has a slightly different configuration. So going from Rev dash to Rev A, we have the same outer race. That's the same outer race. This is the same part number. We don't want to copy this and make another copy of it into here. We want to reuse this. So we say that this part number is part of both of these configurations. However, we've modified the studs and the bolts in here to go to the locating pins. So that's a different variant. We've substituted now this for this new variation of part number. Then when we go to the next revision, this is no longer the same part. This is actually a different part. So we've got one part used twice here and another part used. We've got this same part used once here, but another part here. If we were to try to do this with traditional file-based CAD, we would have actually made a copy of this here, and we would have made a copy of this guy over here. And now if we ever have to go back and modify these, which copy do we modify? Do we modify the copy that's here? Do we modify the copy that's here? Or do we have to modify both of them? So configuration control solves that problem for us. The next thing that we get is change management and design review. So you can see what's happening here is we're having a design review meeting where one of the team members, Mark Kiger, has told us that he's found some new photographs that show that this cutout that we have down here, right here, that this cutout is wrong. On the inner skin, this cutout should only be this rectangle here, and this area right here should be filled in. So we're having a design review where we can completely annotate, capture everything that's wrong. In this case, we're going to another issue where you can see that our holes line up here, but if we follow the blueprints exactly, we've got a mismatch between these holes on the mating. So we can document all of these issues in the design review and say we've got issue number 1, issue number 2, issue number 3, and these need to be resolved. And we can do a formal change where we document those and say these things need to be changed. Rob needs to change this bar, Mark needs to change this, and we can track those changes formally. We can always go back. Another problem, you would ask questions with the file-based people, why did you make that change? Why did you go from the threaded stud to the pin? And they don't remember, and there's no history. What the database does with 3D Experience is it allows us to permanently capture and track all of these changes permanently. We can always go back, we never forget, we can always see exactly what those changes were and why we did those changes. So what kind of teams do we need for this project? Here we have an example of putting the motors into our neck race. We've got the motors, we've got encoders, we've got, when it zooms out here, we've got the Nvidia Nano board, and then we got an Adafruit motor controller. This project is going to be taking the neck race system and creating 3 ROS nodes that allow this neck race to turn. So from our head node, we're going to have an instruction that comes in on one of the nodes that says, okay, we've recognized that somebody's in a stormtrooper costume and they're standing over here, and we want you to turn your head to look at that stormtrooper that's standing in the corner. So the first thing we need to know is, where are we right now? So node number 1, ROS node number 1, is going to be the encoders on these motors that give us what's the absolute current position. Using that absolute current position, we're going to have another node that does path planning to say, okay, I have to rotate my head this direction by 45 degrees. And it's going to put those instructions into place to say, I want to go 1 degree at a time, check my feedback, go another degree, check my feedback, go another degree, check my feedback, until I get to where I want to be. Each of those degree turns is talking to another node, and that's node number 3, and that's the node that's actually driving the motor controller that engages the motors. So for this example project, we want to rotate our head to a set position. We've got 3 motors with encoders. We've got an embedded system, and we got our motor controller, and we want to write in C++ 3 ROS nodes that do each of these functions talking together through the ROS head node. So what kind of team do we need? Here's an example team. Say we've got a team that's at a community college, and this is a college professor, and she's got a team of 5 students, and they're going to implement that neck rotation system. So we would have 5 students that are logged into the platform, as well as the team leader, who's the professor. And we also are going to have a Dassault Systems team mentor on each of the projects that the team lead can talk back and forth to. They can ask questions, they can ask for help, they can submit questions for best practices. And each team will be in this format where we've got the team leader, the team, and then a Dassault Systems team mentor. So what kind of skills are we looking at to do something like this? If you're joining this team, you're obviously going to need some mechatronic skills. We're using the ROS operating system, and depending on how complex of a project you're doing, you may need some pretty heavy-duty robotics background. These are 3 classes that are on edX right now that are either free or you can pay to be certified. I've taken the robotic operating system class, I've taken the robotics class, and I'm currently in the mechatronics class. The mechatronics class is actually a new class that's at the introductory level. This is going to teach you all your electronic stuff, what a motor controller is, capacitors, Ohm's law, C code to drive your motor controller. They do just a generic operating system to drive that, so it's more of just a concept where you learn the fundamentals. This is the robot operating system done by Dwelf. This is an end-to-end getting up and running on the robot operating system, which is what we're going to be using for this project. And then the third robotics project is out of Columbia in New York, and this is a real in the weeds. This is all the differential equations and math, all the matrix calculations and computations that you need to do things like path planning and articulation. One nice thing about this class, though, is all of the homework examples do use ROS. So that really ties all three of these classes together. So if this was a community college team and this professor was looking for material that was supplementary to bring these team members up to speed, these are three great classes that I recommend. So what are the projects? Right now we have a list of projects. Some of these are already in work with Mark, Ian, Steve, NK Guy, and myself. But a lot of these projects haven't even been started yet. So for example, the leg drop being triggered by ROS, foot steering, logic displays, radar eye, differential foot motor control. This was the head rotation that we used for the example a couple of slides earlier. And then we need somebody that's going to be in charge of the Xavier ROS master node that controls the whole robot. So that's basically an overview of the project and our relationship with the SO and what we're trying to do. If there's any questions, we can field those right now, or we've also got some questions that were submitted before the presentation started. So are there any questions? Anybody have any?
There's one in the chat. Puneet Rat answer is, are there any alternatives to Nvidia hardware? There
are alternatives. There's you can use Raspberry Pi, any of the various flavors. You can use Texas Instrument. That first class that I showed actually isn't using Nvidia hardware. You buy like a $200 board to do the exercises, and that's based on, I think, an Intel CPU. The situation on that, though, is that for the kind of things that we're doing with robotics, these cards, what's different from these are running Ubuntu, but what's different from, say, running Ubuntu on a Raspberry Pi or running Ubuntu on one of these boards, that's what this big heat sink is there's 128 NVIDIA graphics GPUs on each one of these boards. So you can see this one has 128 cores. This one has 384 cores. This has 512 cores. So when you're doing something like image processing or machine learning or anything that's doing matrix heavy calculations, you can do parallel processing using these cores. And you're not going to find those, on a $15 Raspberry Pi board. The real difference between $99 and $15 is the fact that you've got this 128 GPU cores that you can run all the parallel processing on.
Cool. There's another question. Philip say, what about autonomy and batteries?
About battery? Is that the question? What kind of batteries are we using? So that, I'm not sure if I can back up, if I have a picture. Is the question about what's the runtime on the batteries? So I don't know if you can see in this picture, but the original units actually had a removable rear panel. And in this section here, they had a stack of, I think, 3 or 4 batteries. So this is going to be quite a heavy unit. I mean, it's heavy, and you're going to have some heavy motors on here driving this thing around. I'm sure this is going to be, you know, 300 pounds, 400 pounds. But one of the design constraints is this rear panel that you can pull off quickly, and you can pull the batteries out quickly and just put new batteries in on the fly. So if you're at a convention and you run out of a battery, after say you're driving around for an hour or 2 hours, and you run out, you can just pull those off and put new batteries in. This system, the main batteries that are running the system are 24 volts. So I think basically a car battery.
Thank you. Can I add something? Can you hear me?
Yes, yes, yes.
I can hear you, yeah.
Okay. My point, Philippe speaking, my point was more related to autonomy versus processing power. Since you put a lot of electronics on board, a lot of Nvidia things, and was forgetting the motors, but motors, it's even worse. But the total amount of energy needed and taking amount the autonomy you need, I'm not sure you will be able to run 1 hour or 2 hours. That's my point.
Right. And that's that right now. I guess that kind of leads into one of the questions here, what we're using for reference. So one of the questions here is, how is this project different from existing replica R2D2s that we see at conventions like Comic-Con or Star Wars Celebration? So those units, they have a bit of electronics in them, but they're not doing the kind of processing that this unit would be doing. And those are being done by remote control. And sort of the expectation of the community that's out there right now when they're at a convention, I think they're getting like 2 or 3 hours of runtime. So before they swap out the batteries. So that's our goal, is to put enough power in this thing that you're at least equal to what the existing remote control units are doing.
And maybe a second question. Would you be open to have the architecture partially deployed on the cloud? Just instead of putting everything in the robot itself, would it be possible to delegate some responsibilities to cloud processing and to put the minimum needed hardware on it and to be connected over 5G to the processing on the cloud where the energy is less an issue?
Right. So that's on each of these teams. You know, we don't have anything set in stone. If you decided that you wanted to be the group leader for the head node that was running, you know, all the head node processing, and there was a ROS node whose job was to go out to the cloud and submit jobs. ROS has a concept called actions and services. So you can definitely make nodes that say, okay, I want to run an action or a service, and there's nothing to say that action or there's actions and services, and the difference is between whether they run asynchronously or synchronously. Either one of those could definitely be something that node goes and then makes a request to the cloud. So that would be a perfect fit on the head node. That node could have all the services or all the actions, and any of those services or actions that weren't safety related, since they're asynchronous, and some of them like tasks where you're just waiting for the result of a task, but yeah, that could certainly be done in the cloud, especially if it's something that's really computationally intensive.
Yeah,
that's a great idea. Yeah.
We are in the 5G area, and 5G is all about low latency, high bandwidth. This is exactly what the purpose. Low latency, high bandwidth, you can do a lot of things there. And the impact will be less energy needed locally.
Yeah, depending on where all the other teams are located, it may be counterproductive to assume that everybody has access to the same technology, and so sometimes autonomous operation might be better and less.
But I think you could even bring, even if you were in an area where you didn't have access to the full, running in the cloud on something like Watson, right? You're renting time on or you're using free time on Watson, and you've got all this stuff running. If for some reason you're not there, you could still bring a laptop along, or you could have a desk side, sitting under the table 100 feet away. That could still get you most of what you're doing externally. So that is a great idea.
Mm-hmm.
Okay, thank you.
I think the last one question is for Rohan. Are all the design files or blueprints are open to everyone?
Yes. So we are we are probably about a month away from opening the blueprints to everybody. So currently we have, I think, 200 licenses. So people that are interested can send us an email and say that you're interested, just to Robert Jackson at openr2.org. And we can send a email out to you that lets you join the community. And when you join the community, you are then assigned to one of the collaborative spaces. Once you're assigned to the collaborative space, you have full access to everything that's in that collaborative space. So you'll be able to download the CAD models. You can download STL files if you want to 3D print stuff. You saw in that slide, I think there was a slide back here where the blueprint, the original material in this collaborative space for the OpenR2 A New Hope body collaborative space. Not only do you get the geometry, but the blueprints in there as well. If you wanted to download that and print it out and hang it on your wall, or if you just wanted to look it over and see what the blueprint looks like and how it was constructed and what the design intent, you'll get all that as soon as you log into the 3D Experience platform.
Yeah, I think that there's all the questions.
All right, so I guess so how do we get access and contribute to data that's stored in the 3D Experience Cloud database? That was the next question. And I think we just answered that. Just send us an email and we'll get you logged in. There's two kinds of access. There's cloud access where you can run everything from a browser. And there is then what we call rich apps that you download the CAD system onto your PC, and then that CAD system or those applications talk to the cloud database. I believe if you're going to do things like download STL files or download the blueprints, or you're working on the geometry, most of that still requires that you download the full rich app to your workstation. If you're just viewing stuff or participating or making design suggestions or doing change reports or change requests, you can do all that just within the web browser right now. And then we have another, how much does it cost to get started with software and hardware? Well, ROS is completely free. If you're a team member of this project, you get CATIA and Delmia and Simulia and all those, and 3D Experience, that's all free. And then really the only thing that you're on the hook for, if you're one of the people doing the ROS nodes, is that $99 development board from Nvidia. Let's see, is there anything else? I guess that's, if nobody else has any questions, or if there's any questions on here that somebody wants, I think we're just about done.
Can you repeat?
So where do we go?
The email, they're asking if you can repeat again the email.
So that's robert.jackson@openr2.org. So what'll happen is you just send a request, and in the request, if you can just tell us what project you're interested in working on, and whether you feel that you're, you know, a team leader or group leader, or if you're just if you just want to be a group team member, just let us know. And then a quick skill set. You know, obviously what we're trying to do here is that's different from all of the other groups that are out there right now, is we're really trying to take it to embrace STEM, right? We want people that have a background in engineering, people that have a background in programming, people that have a background in physics. We really want to make a real robot. So we're looking for team members that have a solid background in STEM. You know, there's no age requirement, there's no geographical requirement, just that either you have a solid background in STEM, or you're going to jump in and bring yourself up to speed, like with those classes. You know, you certainly don't have to have that knowledge to start with, but it's going to involve a lot of STEM, in the weeds STEM concepts. So if you send that to me, I'll take a look at what you're asking for, and I'll add you to the platform, and I'll add you to a collaborative space. And then you can either log into the web browser and you'll be up and running, or you can download the software to your computer.